So we found out that energy has a very particular meaning in physics, which means the potential to create movement, right? And we're going to now turn to another word that you probably use fairly frequently, work, and we're going to find that it has also a very particular meaning in physics. Work. So if energy is the capacity to move mass, it must be able to create a force that causes movement, right? We know that acceleration can only happen when there's a net external force, right? This force movement connection is what work is about. So go back to balanced rock, and I didn't draw a picture of you up here ruining a national monument, pushing this rock off off its peak. Um, but work can be done on or by a system. And in this case, gravitation is working on this rock. Okay, so gravity is pulling down, the rock is moving down, and it's that combination, the force in the direction of movement, that we call work. In this case, what work is doing, and this is what we can say about work in general, is work converts energy from one form to another. So up here we have a bunch of gravitational energy, right? Gravity works on this rock, and in doing so, converts that gravitational potential energy to kinetic energy. Okay, and it is a direct movement. In order to get that exchange of energy, you need to have work happening. And whatever is being lost in gravitational potential energy is being gained in kinetic energy. And so this idea, this is a real key idea. Work is converting energy from one form to another. So how do we quantify work? Um, well, I said before that work happens when force is acting in the direction of movement. Okay, and that's what this equation says. Work is equal to the force vector. Um, really, this is what's called a dot product, but we're not going to get into that. A force vector times the distance vector, or the um, change in distance, the motion vector, times the cosine of theta. What does that cosine of theta mean? Well, it's the theta between these two vectors. Okay, so if the force and movement are in the exact same direction, then this is 0. And a cosine of 0, remember back with our circle, right? 0, a cosine of 0 is going to be 1. Okay, so if they're acting in exactly the same direction, it's simply force times distance. If they're acting in perpendicular directions, say this is 90 degrees, then I may have a force moving rightward, but if my object is moving up, my force is doing nothing to cause that movement, and so it's not doing any work on it. Okay, so here we can see over here we have a force that's pushing down on the lawnmower, right? Well, not all of that force is going into increasing the energy of this lawnmower, only the force that's in the direction of movement. So we take f cosine theta, which is this component of that vector, and then we multiply that times d, and that's what gets our work. So I said before that work is a little tricky here. Work is only done on a system if part of the force vector is in the direction of movement. Okay. So let's look at this guy over here, which is not me actually, holding a large boulder over his head. Like, we think of this as work, right? He's struggling there. It's a lot of work to hold that boulder up, right? In a physics sense, it's actually no work. And why is that? Well, there's no d vector, right? This isn't moving. So any force that he's applying to that rock is not actually adding any gravitational potential energy to that rock or kinetic energy to that rock. Okay, so it's not moving, and therefore there's no work. Now you might say, why am I sweating? Why is this so difficult?
Well, in a human scale, our muscles are moving back and forth, uh, and they're really activated. And that's actually so. There's some internal work going on in this in this fellow here, but he's not actually doing any work on the boulder. So there's some work that's being done. He's converting the energy of the stored energy of his body into muscle movements, uh, but he's not actually moving the rock, and so he's not doing any work on the rock.